Hello, everyone. My name is Dr. Ajit Karunaratne. I am a professor of chemical biology. Given the methamphetamine or ice crisis in Sri Lanka, which is a serious, which has expanded quietly with, of course, the blessings of many past governments, enabling this growth. Fortunately, the current government is taking decisive steps against this drug mafia, including increased surveillance, arrest, and public awareness campaigns, and is working to eradicate it. From the news reports, I see that they have seized over 3,000 kilograms of methamphetamine. That seems like 1 gram for everybody in Sri Lanka, along with nearly 1,000 kilograms of heroin. This is immense. This cannot be taken lightly. Additionally, the connection between these drug cartels and high-ranking, the former politicians of former governments, as well as officials, have recently come to light. And more names, more and more arrests are ongoing. It has been recently revealed that not only do these cartels smuggle drugs into the country, but they have also been involved in producing methamphetamine or ice in Sri Lanka. Basically, the south of Sri Lanka now people call Iceland. It is highly likely that this operational meth lab exists throughout the island. It's really possible. Today, while applauding the current governments led by the President Anurakumara Dissanayake, I'll be speaking with a renowned synthetic organic chemist, Professor Michael Young, who has extensive experience in synthesizing complex organic molecules, some of which are designed to combat pain while minimizing risk of addiction and abuse. About not giving too much details, however, talking about this methamphetamine making process, dangers these cooks and neighbors of this meth lab face, and serious health and social risk faced by the users of this illegally produced drug. So this is, again, not to encourage anybody to start this, however, to discourage and then show the complex chemistry going into this, and then why anyone should not pursue this. Let's meet our speaker, Professor Michael Young. Mike, can you share a brief overview of your background as well as your experience in synthetic chemistry? And also tell us what sparked your interest in conducting research on these drugs of abuse.
Sure thing, Ajit. First of all, thank you for having me today. If you'll give me a moment, I'll share my screen. So I work in what is known in synthetic methodology. And so first I have to tell you, my work is in the area of synthetic methodology. And what is synthetic methodology? Well, the way I like to describe this most simply is, imagine that you've got a bunch of parts and you want to turn those parts into a car. And to do that, we're going to need, obviously, tools to do that. Well, it turns out when we're thinking about designing new molecules, it's very much the same. We'll have a lot of different molecular fragments that we can access, either through finding them in nature, securing them from petroleum, or building them up from those sources. And ultimately, if we want to turn something like this into a drug, again, we're going to need the chemical tools to do that. So in my lab, we've mostly focused on a variety of different areas, most of which comes down to how can we find new ways of making bonds. Now, a lot of what we've done in particular has been in this area of taking small molecule amine-containing drugs and then trying to elaborate those. Amines are present in 85% of drugs, and so it's a natural fit that if you're trying to make new amine-containing compounds, that many of these may actually be useful therapeutics. Now, where we've been particularly interested in this and where we've really been focused over the last several years is something called the opioid epidemic. And so in the United States, a big issue is that these molecules that were originally used for pain have now become a major source of addiction. This just shows the number of overdose deaths per 100,000 per state. Now, I'm here in Ohio, and you can see that it's not the worst state in the country, but it's usually in the top 3 worst in the country for opioid overdose deaths. And so one of the things that is staggering about this, in addition to the human cost, because hundreds of thousands of lives have been lost due to the opioid epidemic, but most notably is also the economic cost. So the White House currently says that the opioid epidemic cost the United States $2.7 trillion in lost GDP in the last fiscal year. To put that into perspective, the total US GDP for that same period was only $29 trillion. And so we now have a synthetic problem, something that we have made, which decreases our economic output by over 10% or approximately 10%. So as a synthetic chemist, what we're really interested in is what are the types of molecules that people use to treat pain. Morphine is one that's been known since antiquity. Tetrahydrocannabinol and other cannabinoids. People are also interested in those. And then probably the thing that's really driving a lot of these deaths in the United States now are synthetic opioids such as fentanyl. And so from a synthetic chemistry perspective, what we're really interested in is, can we come up with faster synthetic routes to make these complex molecules, typically using something called CH activation, so we can very rapidly stitch just a few linchpin molecule or connections together so we can make these complex drugs more easily. And by doing so, we can now make new derivatives that maybe have.
Thank you so much for that kind introduction to yourself as well as the chemistry you're doing. And when we talk about this particular drug, methamphetamine, as you mentioned about fentanyl and morphine, which are targeting opioid receptors, methamphetamine also targets a same family of receptors called its G protein coupled receptors. So they are activating same signaling in your brain, in particular in neurons and astrocytes. And so methamphetamine in particular actually has very interesting chemical properties, dangerous and interesting. To give you the perspective about this, let's assume, we have a lot of Sri Lankan graduate students in the US. I know you have had some of the Sri Lankan PhD students in your lab as well. They would go probably once or twice during their PhD to Sri Lanka. And that's a very exciting feeling. You can imagine after 2 years of time, you are first time seeing your parents and they are at the airport, and then you are coming out of the airport and first time you're seeing them, kind of create very euphoric pleasure. And if you compare the pleasure of that's pretty significant pleasure. So that would increase about 50% of your dopamine, serotonin, and norepinephrine, which are main neurotransmitters in the brain, compared to methamphetamine, which would increase 1500%, 1500. 1500% in Sri Lanka, we call it 1500% increase of neurotransmitters level compared to 50% in a very, the lively event associated pleasure. If you compare this with the pleasures people would experience during sex, which is about 200%. And compared to anything like even morphine or nicotine, they only can induce the pleasure after 200%. So compared to the normal neurotransmitter level. So therefore, 1500 is an unimaginable level of neurotransmitter accumulation in the brain, which is very difficult to treat. We know drug overdose by fentanyl and morphine, people use the inhibitors of opioid receptor, but there are no such inhibitors for the methamphetamine use. So you have to let your body to handle it. So methamphetamine overdose can be extremely dangerous. So, and as you see, this crisis in Sri Lanka and elsewhere in the world is pretty significant on the economy as well as the next generation of productive citizens. So with that, I wanted to turn to Professor Michael Young again and talk to him about help us to understand methamphetamine chemistry. So can you please explain the basic chemical structure of methamphetamine? Everybody says ice. So it's a crystal as much as we understood, and then how it differs from other substances of abuse, as well as can you also explain what are the most commonly used illegal synthetic routes? Again, not to give too much detail so people are able to make them, but routes of producing methamphetamine. Please.
Yeah, absolutely. So I have some stuff prepared which will address all of those questions, not necessarily chronologically the way you've asked them. So I guess let's start with some of the synthetic methods that people have used to make methamphetamine, and we can sort of answer some of those questions as we go. So first of all,
Professor
here,
Young, I presume these methods all are published and very well-known methods in the scientific literature, right?
absolutely.
Okay.
And so one of the first methods, actually this was discovered in the 1800s, is what is known as the Nagai synthesis. And so over here you can see what is called D or dextromethamphetamine. And that dextro is important because it describes the chirality or the handedness of the molecule. And so if you're not familiar, basically organic molecules can have the exact same structure, but different three-dimensional shape, such that although they can overlap, or so they're mirror images of each other, they don't actually overlap directly. And so it turns out many of your biological molecules, in particular your proteins, which are going to be targets for a lot of drugs, a lot of those molecules have this handedness to them. And so it turns out that D-methamphetamine is actually the drug of abuse. It turns out, at least in the United States, that L-methamphetamine, where the only difference is the stereocenter around this carbon-nitrogen bond, basically instead of that nitrogen pointing up, in L-methamphetamine, it's actually pointed down. That's enough to make it no longer a drug of abuse. And that compound can actually be prescribed, I believe, as a decongestant in the United States over the counter. And so just a very small difference, such as the three-dimensional orientation, is enough to change the pharmacology of the resulting compound. So anyway, what was originally found was that you could take something like ephedrine or pseudoephedrine, and the only difference there is that here we've got the stereocenter where this nitrogen is pointed up, and then we've got an oxygen that's adjacent to it, which can either be pointing up, as is the case in ephedrine, or down, as is the case with pseudoephedrine. And so in either case, you can take this one of these molecules, some type of relatively potent reductant, oftentimes red phosphorus is used for this, in combination with hydroiodic acid, and that can essentially break this carbon-oxygen bond and replace it with a carbon-hydrogen bond. Now, if you're not familiar with the way we draw organic structures, we typically don't draw in the hydrogens on any of our carbons because there's just so many of them. So we know that carbons form 4 bonds. When we don't draw in a hydrogen, we know that everything that's not drawn in is going to be a hydrogen. But there are some significant challenges with this route. The first one is that if you're using red phosphorus as a reductant, you will generate some phosphine gas, H3P. Now, H3P is fairly toxic, but in addition to that, you're typically manipulating these reactions in different types of organic solvent, and those solvents are going to produce vapors which are potentially toxic. In addition, both the phosphine and those volatile organic compounds are going to be highly flammable, and so it's proposed that something about 15% of all meth labs in the United States are discovered simply because they catch fire. And that is a staggering number. In addition, the waste that is generated from this process is very toxic. In particular, you end up with a lot of metal salts that are not good for the environment. And especially if you've got a large-scale industrial operation, those have to be disposed of somewhere, and oftentimes they're just disposed of locally. And so what you'll find is not only are these toxic to the operator, the person who's doing the synthesis, oftentimes we'll call them the meth cook, but in addition to being toxic to the meth cook, they can also be toxic to children and mothers and elderly folks in the community.
So that means that if anybody has any indication that there is a meth lab operation, or there's suspicions of having a meth lab operation in nearby, it's actually their best interest, because unborn children, pregnant mothers, most vulnerable people in this community can be at a huge risk. And also, like, if these cooks, so-called, those people making this drug, meth cooks, I don't think they are environmental conservationists. So they will dump their toxic materials into rivers and other, water sources, and therefore the drinking water can be contaminated as well. So is that a fair, reasonable assumption, Professor Young?
Absolutely. One of the other common ways to make methamphetamine is to use what is known as reductive amination. And there's actually a variety of different ways that this can be done. But if you've ever seen the show Breaking Bad, a large part of especially later seasons of that, they're always looking for methylamine. In fact, there's one case where they famously heist or have a heist where they actually steal methylamine out of a train tanker. And so the way that this works is you start with phenylacetone. Sometimes it's called phenylpropanone or phenyl 2-propanone. And what you do is you essentially use the fact that nitrogen is nucleophilic. It can form what is called an imine via condensation. And it's called a condensation because water literally condenses out of the reaction. And then we can take the carbon-nitrogen double bond and we can reduce that. Now, most of the time when we do a carbon-nitrogen double bond reduction, we are making a chiral center. And so we can add our hydrogen from either side of that. And so as a result, whereas in the Nagai synthesis, we made D-methamphetamine, here we're going to make something called racemic methamphetamine. And it's racemic because we're going to have typically a 50-50 mixture of that D-methamphetamine, which remember is the drug of abuse, and L-methamphetamine. Typically, reductive amination gives you a less pure product. The benefit from the perspective of meth synthesis is that whereas ephedrine or pseudoephedrine are typically only procured from pharmacists and in relatively small amounts, the overall amount of methamphetamine you're going to be able to make using those as precursors is probably pretty low. But if you're willing to go this reductive amination route, now a lot more bulk chemicals can be available for your synthesis. The other thing that you need, obviously, for this is going to be methylamine. One thing that's notable about methylamine is it's a gas at room temperature, and so you can't just go and buy methylamine, typically. You're typically going to find it either as its hydrochloride salt. There are some applications for that. Much more likely you're going to find it in solution. And in fact, it used to be the case, maybe in some places it's no longer available because it can be used to make methamphetamine, but you used to be able to buy it as an aqueous solution at a lot of garden stores, for example. Again, maybe that's not available anymore. You can also find solutions in a variety of organic solvents, and those certainly find a home industrially. You still need a reductant in this case. Probably the easiest is sodium borohydride. That is probably not the most easy chemical to get a hold of, but again, things like phosphorus, other types of common reductants that you can find will still work for this. Again, you're still going to get toxic gases, most notably those VOCs. If you have any type of a hydride reductant, and again, you ultimately have to add electrons to this. The hydrogens can come as hydrides or they can come as protons from an acid source, but either way, if you're generating those reductants, they're potentially going to generate hydrogen gas, and then that is obviously a very significant fire or explosion hazard. And in this case, again, there's some toxicity to the waste.
When they make this, using this reductive amination, when they make this racemic mixture of methamphetamine, do you think these cook separate the D and the L versions and then only sell the L, or mostly in the market what you would see is the racemic mixture? You don't really even know what are those proportions.
Right. So in general, whenever you're looking at the illicit drug trade, I would say no. These people never know what the purity of their compounds are. And this may be a little bit surprising based on popular culture, because if you've seen Breaking Bad, they always talk about 99.1% purity. But the reality is, meth cooks generally aren't going to know what the purity of their compounds are. In chemistry, we have a variety of different ways that we can test purity. The simplest is doing something called a melting point analysis, but that doesn't tell you that your compound, it doesn't give you a measure of the purity other than just if it's very high purity, you'll get a very sharp melting point. If the purity is less, the melting point will decrease, but there's no way to correlate that melting point or range of melting points with an actual purity. In chemistry, what we'll do is we'll use something called high performance liquid chromatography or NMR spectroscopy to determine purity. Those are expensive instruments, and HPLC probably is going to run $50,000 for a new one, and that's with an academic discount. So you can imagine realistically $100,000+ US. I can't imagine that your average meth cook is going to have access to that type of equipment. Meanwhile, something like an NMR spectrometer, those are probably going to be $1 to $5 million US. And they require cryogens, in particular liquid nitrogen and liquid helium, to work properly. And so I imagine, again, that's not something that your average meth cook is going to have access to. So yeah, absolutely. There is not really an easy way to tell what the purity of your amphetamine is going to be, your methamphetamine product. And even aside from that, it's well known that a lot of times you'll make up the weight with other compounds. And so in this country, it's well known that if you're going to take an 8-ball of crystal meth, for example, well, it could have fentanyl in it or some other compound that maybe is more potent, where they can sprinkle a little bit of that in either to make up the balance. Sometimes there'll be things that are not active but are potentially hazardous, such as lead oxide compounds. Again, there's all sorts of things that can happen. The people who are selling you drugs, aside from not necessarily knowing so much chemistry, also don't have your best interest as the end user in mind.
It's very famous that the Golden Triangle in Southeast Asia is kind of really no democracy and no government ruling in these areas, and they have this very complex operations to create either directly the drug of abuse or the materials. So could you, if you were to anticipate, could you anticipate that it's possible that some of these precursor materials are being synthesized in these kind of locations and then send it for the final, for instance, final 2-3 reactions in a local meth lab in Sri Lanka in some place?
Absolutely. And I do have something to discuss about other types of precursors that can be used. And the challenge is that there's a lot of different ways that you can make meth. If you have no experience in chemistry, then you're probably going to be limited to only the recipes that someone has provided for you. But even with a mild college level exposure to organic chemistry, you can absolutely come up with probably at least 10 or more different ways to make methamphetamine. And so what typically is seen is that some of these operations will always be looking at what are the available resources and then determine a way to make meth based on that. So absolutely. If you can't import methylamine, well, you can import things that can be converted into methylamine.
Methylamine eventually. So right. Basically, like large industries, like maybe manufacturing of soap, of fabric, because Sri Lanka is very famous for garment industries. So they have all the fabric softening reagents, variety of different chemicals they are being used. So I think those are the places I would assume that law enforcement is looking and to see whether if all the stocks arrival inventories are properly inspected and managed, and then how these things are being whether if these things are being smuggled out of those places. So again, you briefly mentioned this, so I wanted to ask you, because when I look at this chemistry, this is basically graduate level. In Sri Lanka, we call it like postdoctoral level chemistry is needed to run these reactions. And also, if you wanted to purify them using a complex method like liquid chromatography, like HPLC, or preparative chromatography that is used being in the pharma industry. So it's possible that I'm almost certain that these meth cooks are not actually university graduates. In Sri Lanka, we call it university instead of college, university graduates. So they are just basically mostly, I presume, street thugs, or people actually are visiting Sri Lanka. That's possible, like, as tourists, has experience, and then being hired by these drug cartels because they have large sum of black money to earn through these operations. So it's possible that the foreign individuals that are being the cooks of these drugs. So can you please elaborate a little bit on alternative routes of methamphetamine use if they could not find ephedrine or pseudoephedrine?
Certainly. And even phenylacetone can sometimes be a challenge. And so, looking into things that are maybe seem more innocuous but could still be diverted for meth synthesis. Two that are particularly noteworthy for the sort of phenylacetone precursor are phenylacetic acid and then ethyl phenyl acetate. Both of these find use in particular in the cosmetics and fragrance industries. And so In particular, these can be used to make things that have the flavor or scent of honey, as well as jasmine. Something that's probably used in a lot of teas and again in a lot of perfumes. And so these are two very easily diverted chemicals. In particular, there's a route where you can take phenylacetic acid, which can either be used directly or you can prepare it from here. You can react this at a very high temperature with just simple acetic acid that you can get from vinegar. And you can now actually make phenylacetone in one step. It's actually a very reasonably clean reaction to do. In addition, obviously methylamine is very important. Well, it turns out we don't actually have to use methylamine directly. We can use something like N-methylacetamide, which is a common industrial solvent. Probably it's used in some of that textile manufacturing, in particular for some types of dyes, which may not have very good water solubility. I know its use is becoming phased out in Europe, probably in the United States, but I imagine a lot of Southeast Asia, it's still quite readily available. And so it turns out that you can actually very easily break this carbon nitrogen bond, and you can see then that there's methylamine just sitting there waiting for you to use. And so you can actually directly use this in the reductive amination. It turns out it requires a much higher temperature, but it does work. The other thing that's convenient about that is that N-methylacetamide is actually a liquid, so it's actually much easier to work with. However, we can also directly make it from some very, very readily available compounds. For example, we can take formaldehyde. Formaldehyde obviously used in the embalming industry. It's probably also used in a lot of agrochemicals, and it's probably used a bit in the tanning industry, if not more broadly speaking in the garment industry. But in addition, we would use ammonium salts. And it turns out the ammonium salt you use doesn't specifically matter. Ammonium chloride is probably the most common, but ammonium acetate, formate, any of these could also be used. And so ammonium salts are very readily used as nitrogen source in fertilizers, either ammonium or urea. You can also make ammonium salts directly from urea. So again, there's a lot of opportunities to get to these two components. And it's probably very hard to regulate them because they are so ubiquitous in a variety of different industries.
Thank you. The public in general, the understanding, because when the government sees drugs, you see the powders, right? Either heroin, crystal meth, or methamphetamine we are talking today, or ice, and they all are powders. So people always anticipate that in these ingredients to make these drugs are powders. Is it true?
So it turns out that whenever you've got a compound that contains an amine, they tend to have very low melting points. And there's some interesting reasons for that based on how nitrogen-hydrogen bonds. It's a weak hydrogen bond donor. It's a moderately strong hydrogen bond acceptor. But the reality is that they don't tend to crystallize very well. And so a lot of times when you have any type of amine-containing drug, we don't actually use the free amine or the free base. Probably this is most familiar in the term of cocaine, where you're familiar with the term crack cocaine and then free base cocaine. But generally speaking, we don't use the actual free amine as the drug. It can be done, but it's not typically done. And so in the case of methamphetamine, this is absolutely the case, where we don't usually have the free base amine. We instead have the hydrochloride salt. And that actually adds another element of complexity and potential hazard. And so what I've shown here is if we take the D form of methamphetamine, we can simply add hydrochloric acid, sometimes called muriatic acid, to that to make the hydrochloride salt. Now, this is not exclusive to HCl. You could add any strong mineral or even organic acid and do the same thing. So for example, you could crystallize this probably with citric acid, with tartaric acid, right? Some fairly readily available organic acids. And so what this does is it takes the methamphetamine, that free amine, which again doesn't really crystallize very well, and it now dramatically increases the melting point so that you can now get a nice crystalline solid. The challenge with this is now you're going to add, at least if you're using HCl into the mix. Most of the time, HCl is sold in aqueous solutions. But the problem is HCl is a gas, and especially from a highly concentrated solution, that gas is going to be liberated. It's a corrosive gas that can very readily burn the lungs, any mucous membranes. So a lot of times when people are making methamphetamine, they're going to be doing this closed up because there are all these terrible odors that are coming out. It's pretty obvious that you're doing something illicit or clandestine. The problem is that, if I'm doing a synthetic reaction in my lab, I have fume hoods, I have good ventilation. But if if you have one of these labs and you don't have good ventilation, you're basically being exposed to all of these chemicals just constantly. And so it will definitely shorten your lifespan, even just if you're the cook.
So, Mike, is this chemistry allows use sulfuric acid instead of hydrochloric acid?
You could absolutely use sulfuric acid as well. You'd get a different product. But yeah, again, any salt in principle could be used to crystallize this out.
Right. Yeah. The reason I ask is sulfuric acid is much more prevalent compared to hydrochloric acid because of the battery industry. Mm-hmm. And it's funny you mentioned the muriatic acid, or it's about 30% HCl that's sold in hardware stores in the US, where you use them to actually clean bricks. So you can dissolve all the masonry cement using muriatic acid or HCl. So you can, the viewers can understand how powerful and toxic these acids are. Okay, I wanted to ask you in the general question about your opinion that now the Sri Lankan drug enforcement agencies, huge effort is looking for any form of meth being imported or being produced, stored in Sri Lanka. And so as you can imagine, this crisis apparently came out of nowhere because the former governments, the previous very high-ranking elected officials publicly supporting those people accused for importing drugs into the country. And therefore, it was really hidden under the rug. And then until probably last few months, we did not know the crisis was so bad. Even the law enforcement, they have to train so many personnel to perform these raids and take this into custody. So I wanted to ask your opinion. What specific indicators should law enforcement and community members be aware of identifying potential meth lab or meth during these kind of operations?
That's an excellent question. I've prepared here just two pictures I've actually stolen off of a simple Google search, so my apologies for the citations on that. But what's really surprising is just how, at least to me as an American, and maybe this would be accurate for Sri Lanka as well, how many of the things that you can use to make meth can actually be sourced from readily available things. So we talked about reductants. Well, here we see that we've got some lithium-ion batteries. Lithium, in this case, can be used as a reductant. We see ephedrine or pseudoephedrine here. And again, these are pills that can be typically purchased over the counter. In the United States, these are heavily regulated. You're carded for these. A store will keep track of how many you buy. But the trick to get around that is that you may have what are called Smurfs, or maybe gophers, another term. Basically, you'll get a lot of people to go in and buy the amount that they're allowed to buy and then pool them all with the meth cook. And so I would say agents would need to be aware of those types of practices. Those are probably the straightest forward way to make meth is to get those ephedrine or pseudoephedrine pills. But, other things such as buying muriatic acid, again, if you've done construction, you'll know how readily available that is. So it's going to be really difficult for some of those things. So I think the things that are going to be the easiest to police are going to be really those precursor chemicals rather than some of the supporting reagents. Things like ephedrine, pseudoephedrine, because again, everything else is kind of hard to police. We can't really police, for example, red phosphorus. Where does red phosphorus come from? Well, there's a lot of products that have it in them, most notably matches, right? And so, unfortunately, those are things that are really difficult to police. So those precursors are going to be the easiest thing to look for.
So I see a lot of different chemicals in this picture, including like salt and then starting fluid. Is kerosene is what it means by the starting fluid or something else?
So typically starting fluid is going to be an organic mixture. And so what starting fluid is most likely going to be used for, similar to acetone, or to, ethanol, is going to be that it's a solvent, right? So whenever you're doing organic reactions, you have to have a solvent. The problem is water is a solvent for a lot of biological processes, but it's not necessarily a great solvent to work with chemicals in. It can be done, but water is very hard to evaporate. And so we typically will use organic solvents. Acetone is very popular. Diethyl ether is very popular, but also hydrocarbons like toluene and xylene. And that's probably what you're actually seeing in the somewhat in the starting fluid. And these organic solvents are necessary to do this work. They also add a lot of the hazard, because if you're working in a meth lab and there's poor ventilation to no ventilation, as the concentration of those volatile organic solvents builds up, the flash point for them is actually typically below room temperature, well below room temperature. And so what that means is any type of ignition source is enough to set the whole place ablaze, right? And what could that be? You decide to smoke a cigarette too close to the vapor. You have a burner because, maybe you're using a Bunsen burner or some type of open flame to do your heating. That's enough. I've heard of stories of even electric elements being able to spark and cause
the tiny spot.
Right. So that's all you need once you have a buildup of these vapors for the whole thing to just go up in flames quite rapidly.
So that's really remarkable to know, though we really probably not thinking that how many chemicals are around our lives every day-to-day life. And my fear is that when the government start having all these patrols around the country, in the ocean, everywhere, at the airports, and being an island nation, so there may be an there may be an increase of seeing illegal meth labs around the country because it's very harder to smuggle them in. So I see on your right side image some jars and glassware. So I wanted to ask your opinion about the places you would find this glassware, and operations are basically like medical laboratories, school laboratories, and universities and technical colleges and that sort of places. And Sri Lanka is just becoming digitalized gradually, and inventory management, I don't think up to speed. And with money, people do a variety of things. So you think there could be like institutional heads, even school principals, science teachers. For instance, the Breaking Bad, the TV series you mentioned, the PhD school chemistry teacher with PhD is the cook. So therefore, I wanted to ask your opinion about, or your advice to the institutional leaders who has laboratories under their supervision. What should they be looking for in coming months and years in Sri Lanka that could be illegally used to make meth?
Well, I think the picture on the right actually shows that you don't really need anything quite so technical, whereas in a laboratory, I would use things like an Erlenmeyer flask or a volumetric flask or a volumetric pipette to accurately measure things. The reality is that if you need, we have many things that can actually do measurements, and maybe they're not as precise, but something as simple as a coffee pot can be used to reproducibly synthesize meth And so I think the thing that's really the takeaway here is that you really can't easily police that. And so again, the two things that I would say you really want to be focused on to control this is going to be those precursors that you have to have and that can be easily regulated. So again, that Nagai synthetic route, if you can shut down the access to those precursors, then you're going to really force people who want to make meth anyway to find those other routes. Then if you see private citizens that are buying large amounts of phenylacetone or the precursors to that, then maybe that's worth some additional look. But again, that'll be challenging, and you could probably have, if your inventory management's not good enough, you'd probably have small amounts of those going out. So realistically, my advice would be this. The best way to control domestic production of methamphetamine is simply to initiate an education campaign. And it's not for the meth cooks themselves, because they probably won't care. But who will care are all the people in the community who are going to be negatively affected by this going on in their backyard. Not just because of the proliferation of methamphetamine, which obviously is going to be harmful to the entire community, but the fact that so many of these production facilities will be releasing toxic vapors. They'll potentially be catching on fire, right? And if the house next door to yours catches on fire, your family is at risk. And I think the thing to do is especially design this education campaign so that if people believe that meth is being made in their area, they should step up and say something about it, because otherwise they are in danger many different ways. Not just from the fact that there's a drug cartel around, but the fact that there's significant danger of having all those chemicals around.
Excellent. In particular, like you see, along with your advice, that these meth cooks or the drug cartel members, they have enough money to throw around, and then they would probably pay unreasonable rents of renting properties, unreasonable prices for renting properties. And then if you see such, or if you experience such things, always it's actually you have the rights to be suspicious and then make your background check before you commit. Because one of these meth lab explosions simply decimate your property, right? You will no longer, it can be a tremendous damage, physical property damage at the same time, and you will be probably prosecuted against, allegedly supporting the meth lab operations. So thank you so much, Professor Michael Young, who is a professor of organic chemistry at the University of Toledo, is speaking with us today, helping us as, he has had many Sri Lankan graduate students in his laboratory, so he knows about the country pretty well. And therefore, we really appreciate his time explaining the complex chemistry and the dangers around this methamphetamine synthesis, explaining to us. So we hope the Sri Lankan public and the law enforcement could use some of this information in our combat against this devastating crisis Sri Lanka has experienced. And so with that, thank you very much, Professor Michael Young. In another discussion, we will meet like this again. Thank you.
Right. Subharatri.
Wonderful. Subharatri.